Hey there, this is Intro to Malloc, and we're talking about bins this time. Bins are the thing that I kept alluding to in the previous solution guide, and it's really hard. It's a chicken and the egg problem whether you talk about chunks or bins first, but I just chose chunks. So we're talking about bins. Cool. So what is a bin? A bin is a group of pointers to free chunks. And they're organized in the form of linked list head and tail pointers. So in this diagram here, we have a bin. There we go. Okay. We have this bin. And it has a head pointer to the first item of the linked list. It has a tail pointer to the last item of the linked list. Effectively, bins are just pointers to beginning and ends of linked list. There are both singly and doubly linked lists in Malloc, though. There are many different types of bins that hold many different sizes of chunks, and they serve different purposes. However, it's important to know that all bins start empty. Everything has to come from the initial SBRK allocation. So there's a lot of information here, and I'm being honest, and during the workshops I gave at DEF CON and various other conferences, I actually gave out a cheat sheet just to remember this stuff. And you guys should have access to that cheat sheet. It should be in the repo. But these are the things I always said were really important for the course. But this is more an advanced thing, and you have more time to go through it. So I think it's okay if you want to go through a little bit more. And I'm going to spend more time on some of the other concepts. But the really important things you need to know about a bin, are what type of data is stored in it. In particular, what sizes are used. What type of linked list is it, singly or doubly? And what type of ordering is it? Meaning, is it last in, first out, or first in, first out? The first one is the T-cache bin. The T-cache bin is the most simple. The T-cache bin is a thread-specific cache, and it is the first location that chunks look at. It is a singly linked list, and it uses last in, first out for its mechanism for taking out. What I mean by that is it's like folding clothes. If I free a bunch of chunks into this particular bin and I need to get one out, which chunk comes out first? And it's last in, first out, which is like folding clothes. If I stack clothes on top of each other, I grab the one off the top. So the last piece of clothes that was folded is the first one that you take off. And that's how this works as well. The last chunk freed in that bin is the first one that will come off. Now, there's not just one T-cache bin. There is a single T-cache bin for each size of T-cache. Now, this ranges from hex 20, hex 30, hex 40, all the way up to hex 410 in size. Unlike other bins, the T-cache is actually limited amount of chunks that can be in it at 7 chunks. For whatever reason, they decided to overload what a chunk looks like with T-cache. The FD is now called next in the Malloc source code for some reason. And then the key, which would normally be the BK field, is no longer used because it's a singly linked list. So it uses it as a double free protection. Now this is what it looks like if we have things in all the different bins. Notice that each size of T-cache and hex 10 or 16 by increments is what we're looking at. You see hex 20, hex 30, all the way to hex 410 in size. Now, the T-cache itself is allocated to the heap, which is kind of funny. It's usually the first entry in the main arena. We'll talk about the arena stuff later. Now, it has a list of counts and a list of entries. The entries is going to be the first item in the linked list, and the counts is an array that keeps track of the amount of chunks in a particular bin at that point. Now the fast bin was the first optimization that was made. The idea is that we want to handle chunks of very small sizes. It's really common to allocate something within the hex 20 to hex 80 range. Like T-cache, the fast bin is also last in, first out, which is like stacking clothes. With both the T-cache and the fast bin, there's no coalescing. In particular, this means that we don't combine adjacent chunks. all three of the bins after the Tcache and fast bin will combine chunks that are adjacent to it. And practically there's nothing that actually says, hey, this is a fast bin chunk, don't do that. What it actually does is it checks the prev and use bit. And if the prev and use bit doesn't, it just doesn't update it. So if I have a chunk ahead of me, sorry, if I'm a chunk that's getting freed, instead of setting that chunk to be 0, which is what the coalesce process needs, it just doesn't do that because we don't want it to be combined. It's kind of a hack in the source code, but it does work. And that's why the tricks I was doing before in the solution guide were working the way they did. The next one is the unsorted bin. So the unsorted, small, and large bin, which we're going to talk about, were kind of the original bin types that were within Malloc. Now, the unsorted bin can have chunks of all different sizes, and it gives memory another chance to be used. Prior to the fast bin and Tcache, this was the first place that something went, and it holds chunks of all sizes, which is unique. Everything else has a specific size range. The other thing that's unique is that it's first in, first out. What does this mean? In contrast to last in, first out, which was like stacking clothes, first in, first out is like waiting in line for ice cream. The first person who was in line gets their ice cream first. You go to the back of the line, and you would be the last one in that case. So there's only a single unsorted bin. Now, it's kind of interesting in itself, but it's a doubly linked list, and it supports combining adjacent free chunks. Now, I have a small slide here on coalescing, but we really hammer home how coalescing works in the unlinked module because we're actually going to exploit the coalescing process. So at a high level, though, if we have adjacent free chunks, we want to combine them. So if the chunk below me is free, then we just make it into one big chunk. If the chunk above me is free, then you also combine them. The one exception is if it's the top chunk, then it just takes that chunk and puts the data into the top chunk and combines it. Now the small, large, and unsorted bins will always merge chunks together if they're next to each other. The next bin is a small bin. A small bin holds a single chunk size per bin, like we talked about with the other ones as well. It's a doubly linked list, so that's this is like the standard doubly linked list thing as before. The one thing that's weird about doubly linked lists, though, is what do you do with the BK or the ending BK? Sorry, the beginning chunks BK and the ending chunks FD. You could set it to null, but for whatever reason, Malloc decided to point it back to the bin. So in future modules, we'll actually exploit that fact because it's really nice for getting libc leaks and heap leaks. Again, the FD and the BK is in the linked list structure inside the chunk. This is the same diagram I showed before, but instead of Tcache, it's now small bin. And the FD and BK are just doubly linked list pointers that go between them. The large bin, gosh dang it, is there a better image there? Poop. This slide's annoying, but we will make it through. I will turn off my video for a second so you can see. So here, the chunk has 6 fields now. For large bin chunks, there are 2 extra fields. The FD and the BK are exactly the same as before, but the FD next size and BK next size are interesting. Unlike the small bin, the large bin actually holds a chunk size range, meaning that we don't want to have hex 200, hex 210, hex 220. Instead, a single large bin will hold a range from hex 210 to maybe hex 400 or something. So the large bin needs to be ordered as a result. And this is kind of interesting. So the FD and the BK fields act as pointers to the next chunk that's ordered in the linked list, but the FD next size and BK next size are pointers to the different sizes of chunks in the linked list. So this is really helpful because I don't have to go hex 210, hex 210, hex 210. I can go, oh, is hex 210 big enough for what I need? No, I'm going to jump all the way forward now. And another interesting optimization is that the large bin is last in, first out on the second item. The reason it's on the second item is because we don't want to have to rewrite the FD next size and BK next size of the chunks that are in that stage. So it only has to rewrite a couple of pointers instead of a bunch more. So it's a small efficiency thing. So this is a nice picture of the large bin distribution. I stole this from Azaria Labs. Full credit goes to them, and I'm pretty sure there's a link in my slides to that. So the first 32 large bins have a spacing of 64 bytes. The next 16, it's 512. The next 8, the spacing's 4096. And it gets bigger and bigger until it's so big that we just have one to rule them all. I think I actually stole this diagram to the intro to, like, there's actually like a Malloc document within glibc, and I stole it from there. And I think this shows it pretty well, where we have a size of 132, and then 120. So the forward and back pointers point to each other, but in the FD and BK next sizes go to the next differently sized chunk in the linked list. And this allows us to more effectively iterate through the list. Cool. So now I can turn my camera back on. Hope you guys weren't too sad you couldn't see my wonderful smile again. Cool. So now we have a couple of questions again. What's unique about the unsorted bin? What type of linked lists are in the following bins? And that is unsorted, fast, and Tcache. Wait a second. I don't know, maybe I'll check my phone real fast while you pause. All right, we're good to go. So the answers is that the unsorted bin is kind of like a recycling bin. It has chunks of all different sizes in it, and it was the original place that things went. For the linked list, the unsorted bin is a doubly linked list, and then the Tcache and fast bin are singly linked list. And those are the two most common bins we use for exploitation, so it is important to know those the best. Cool. So that is the section on ordering. On bins. The next section is on ordering. Thanks for listening in.